weeks. Again, this is Sail Martha's Vineyard. You've joined our winter lecture series, and tonight we have Brian Whitley with Weather Routing Inc. He's up there in one of the boxes on your screen if you've got Zoom set up with that Hollywood Squares format. I'm going to soon turn it over to him. I just want to let you know that it's really great. I've seen a lot of nice donations come in, and thank you so much. Your contributions have helped support the Sail Martha's Vineyard Winter Lecture Series and also our other programs, and they are greatly appreciated. Of course, one of the things that you're helping to support is our summer sailing program, which is we're signing up kids left and right. So please renew your membership, go on our website, check out the summer programs. We have everything for kids from 8 years old to adults, and you can sign up for private lessons in the afternoon.
Yeah, right.
We also have windsurfing, and we have other great programs like our rowing program.
Confirmed by.
Again, please, anybody who hasn't done so, please mute yourself if you could, and refrain from talking during the talk. If you do have a question, save it for the end. And we also have a chat box. I'll try to monitor the chat box, but I can't guarantee we'll be able to get to all of your questions. So I'm going to turn it over to Brian, and we're going to have people still joining us here for a few minutes, Brian, but take it away.
All right, thanks so much, John. I'm going to just kind of get right into things here. This is going to be a talk about weather basics. So for some of you, this information you may already be quite familiar with, but hopefully for a lot of you, you may learn something that you didn't already know. And of course, as John said, I'll certainly be able and willing to answer any questions you might have at the end of the presentation. So without further ado, I'm going to share my PowerPoint here and get right into it. So again, as John said, my name is Brian Whitley. I'm an operations manager and a senior meteorologist here at Weather Routing. We're located in Glens Falls, New York, upstate New York. And we were founded in 1961, actually founded by a meteorologist who worked for the US government as a meteorologist during World War II. And after he got out of the military, he moved to Manhattan, founded Weather Routing, and ultimately, I believe it was during the 70s, the company moved up to Glens Falls, New York, and that's where we've been located ever since. We do forecasting for a wide range of maritime interests. That does include, of course, sailing vessels such as yourselves. We do forecasting for yachts. You know, the part of the company that I work for does specialize more in forecasting for sailing vessels, pleasure vessels, yachts, things of that nature. But a bigger part of our company, about 2/3 of our employees, forecast on the commercial side of our company, and they're forecasting for cruise vessels, cargo ships, offshore supply vessels, things of that nature, as well as marinas. So here's what we're going to be talking about. Not just the company, of course, but we will get very shortly into talking about the weather. We'll talk about climate and the differences between weather and climate. Sometimes those terms get used interchangeably. We'll spend a good amount of time taking a look at surface maps and how to interpret weather charts, and also briefly talk about upper level charts. We'll talk about reading observations. We'll talk about radar and satellite data, how you can read the clouds and how the progression of clouds can help you do some short-term forecasting. And we'll also talk about ocean currents. So we're going to start right at the basics with the question, what drives all of the weather? And the answer is, well, it's quite a distance away. It is, of course, the sun. And the sun, the biggest thing about the sun in terms of the weather and how it drives it is that it, of course, affects the earth and heats the earth significantly differently at different parts of the globe. Of course, at the equator, the rays of the sun are coming in at a right angle and heating the earth there quite a bit more than the rays that are coming in at the polar regions, where those sun's rays are hitting at more of an angle. And of course, you're getting less heating at the polar regions. And the earth doesn't like uneven heating, and it does its best to redistribute that heat. And the two main ways that it does so is through the atmosphere. Of course, air masses moving from north to south and vice versa. But a more significant portion of that is actually the oceanic currents. And again, we'll talk a little bit more about the currents in just a little while. But air masses play a significant role in the weather. And of course, air masses will develop over particular regions. And then when they start to move, again, because of that inequality in heating and in energy in different parts of the globe, those air masses collide. But air masses are classified by the location of where they develop. There's continental air masses versus maritime, land versus sea, or land versus sea. There's then the temperature of those air masses. Tropical, of course, air masses that originate from locations that are closer to the equator. And then as you go north or south in the southern hemisphere, you get polar air masses that occur in more temperate locations. And then farther north, you get into the Arctic air masses. And then you can get several different perturbations of those continental polar air masses or maritime tropical air masses. And it's when those air masses get together and you see those air masses moving, that literally it's the boundary of those air masses where you have fronts, and it's along those fronts that low pressure areas and storms develop. And ultimately, it's the collision of those air masses which creates the weather. Now, the bigger the difference in the air masses, and especially with the temperature, the stronger the jet stream gets. And ultimately, that drives the strength of the low. It lowers the pressure of the low pressure systems or the storms, and that creates stronger systems. And the movement of those air masses, again, ultimately is what produces the weather. Now, weather versus climate. What is the difference between the two? Well, basically, weather is what's happening or what is going to happen. Is it hot? Is it cold? Is it raining? Is it cloudy? Climate is all of that, but it's averaged out over a long period. And you can actually break up climate for each individual area. And you can see here on the screen a classification system. This was actually developed, I believe in the late 1800s. It was a German scientist named Koppen who originally developed this system of naming climates. Is it warm? Is it dry, cold, or warm? Do the temperature and precipitation change on a seasonal basis or monsoonal? You can see at the bottom of that particular graphic, there's approximately 25 to 30 of these different classification systems around the globe. Let's talk about surface charts and how to interpret them. They do display weather features, highs, lows, fronts, tropical systems, troughs, and understanding these features and how to read surface charts can give you a little bit of your own weather briefing. So here's an example of a surface map, and this was generated by NOAA at the Weather Prediction Center. These maps are issued every 3 to 6 hours, and let's kind of break down that map in terms of some of its different components. You've obviously got highs and lows, and we'll start with the high pressure system. Well, what is a high? Well, first you measure the pressure of the atmosphere at the surface, and you've got different different pressures, of course, higher pressure versus lower pressure, and where those pressures are at their highest, that would be the center of a high pressure. And as you'll see in a moment, it's pretty much the same thing with a low, just in the opposite. There's two basic different types of high pressure systems. There's semi-permanent. You've all probably heard of, the Bermuda high. That's kind of an example of a semi-permanent high where the high tends to set up. And the Bermuda high is kind of an extension of the Azores high. But it's semi-permanent in that it is there more often than it is not there. And then there's transient highs. Those highs are often associated with air masses that develop. Oftentimes over land, you'll get cold high pressure systems. Of course, at this time of year here in the Northeast, we're all very well used to those cold highs that come out of Canada. Those are transient highs. What often happens with those is that they move southeastward out of Canada, across the Northeast, and then off the East Coast, and ultimately they merge with that semi-permanent high near the Azores and near Bermuda. The air around a high pressure system flows in a clockwise direction in the northern hemisphere. In the southern hemisphere, it's counterclockwise. And as you're all, again, probably familiar with the high, the big blue wave, you get nice weather, maybe not for sailing, but, nice weather in general near the center of the high, light winds, sunny skies, and it's away from the center of the high that you tend to get the stronger winds. So let's talk about where you can see a high pressure system on the surface map. Again, the big blue H, indicative of nice weather. In this case, we've got the center of the high basically right along the Maine and Quebec border, and then it kind of extends southwestward from there across New England and much of the Northeast. Now, notice encircling that high near the Maine border, there's a brown line. That's an isobar. Those are lines of equal surface pressure. So everywhere along that line, the surface pressure is the same. Now, low pressure systems, of course, pretty much the opposite of high pressure systems. That's where at the ground level, the air pressure is at its lowest. The deeper the lower the pressure, typically the more intense the winds are with the particular system and the stronger it is. But it's really ultimately the difference in the pressure that drives the strength of the wind. When you have a more significant difference in pressure over a shorter distance and area, that's where you tend to get the strongest winds. Now, the air around a low pressure system in the northern hemisphere flows counterclockwise, opposite that of the high, but in the southern hemisphere, they flow clockwise. The isobars near the center of a low tend to be more tightly packed versus what you would see with a high pressure system. And ultimately, as you would often expect, the stormiest weather and the strongest winds are often closer to the center of that low. So here's an example of a low pressure system on the surface map. The low pressure is over northern Mississippi. Again, notice those brown lines that kind of encircle the low. Again, those are the isobars. And to the north and the northeast, those isobars are more tightly packed. You more than likely would tend to find stronger winds in that area as the pressure is trying to equalize itself, and the winds are rushing about trying to equalize that pressure. The pressure is trying to go from higher pressure to the lower pressure. And of course, with these lows, you do tend to get stormier weather in terms of precipitation. All right, frontal boundaries. Here's an example of a cold front, a blue line with blue triangles. And cold fronts are the leading edge of a colder air mass that is moving toward a warmer air mass. Cold fronts are typically associated with showery, squally weather. That's where you're most likely to find thunderstorm activity, is with a warm front when compared, with a cold front when compared to a warm front. And with the passage of a cold front, typically the winds would go from a south or southwesterly direction, and then they would veer to the west and the northwest following the passage of that front. The winds are strongest near the front, so immediately ahead of it, and then again immediately behind it with those south to southwesterlies or then the northwesterlies. More often than not, they're strongest with the northwesterlies. The colder air is able to more easily mix those stronger winds aloft down to the surface. And finally, the triangles on that cold front indicate the direction that the front is moving. So in this case, it's moving southeastward. Here's an example of a cold front on the surface map. There's a low pressure area centered just south of New England or near New York City, with a trailing cold front that extends across the Chesapeake and then across the Western Carolinas. The blue triangles again indicating that motion southeastward, moving off the mid-Atlantic. Here's warm fronts. Same thing as cold fronts, just with warmer air that's trying to move into a cooler air mass farther north. Unlike with cold fronts, warm fronts tend to produce a lighter and steadier precipitation, often occurring over a larger area when compared to cold fronts, which again tend to be more showery, more squally, more significant changes in the intensity of that precipitation. With cold fronts, it tends to be steadier with the warm fronts. As a warm front passes over you, not only, of course, will you see an increase in the temperature usually, but often you'll see a significant increase in the humidity as well. Ahead of the front, winds will often be northeast or east, and then as the warm front moves overhead, you'll see a veering to the southeast and probably actually even more southerly. High winds, especially over land, are not as common with cold fronts. Over the open ocean, that can be a different story. You can get stronger winds to the north of warm fronts over the open waters, but because of friction with the land, you tend to get much lighter winds with warm fronts. And as with the cold fronts and the blue triangles, with the red semicircles that you see here on this map or on this front, they indicate the general direction that the front is moving. So in this case, it's moving kind of north-northwestward. Here's an example of a warm front on the surface map. The low pressures over the western Great Lakes. There is a trailing cold front near Chicago, but a warm front that extends from Michigan southeastward across the Ohio Valley, western Pennsylvania, and then ultimately across the Chesapeake. And again, the red semicircles are indicating the direction. It'd be nice if that was taking place right now. Actually, it more or less is taking place right now. We've got warmer air, of course, heading in our direction here in the Northeast. Made it well into the 50s out here today. So looking forward to tomorrow and some nicer weather. All right, stationary fronts. Basically, a stationary front is what happens when a cold front or a warm front stalls and it stops moving. You've got that difference in air masses from one side of the front to the other, but the front itself is not moving, or it's moving very little. Sometimes we'll refer to them as quasi-stationary. You might see little ripples of movement north and south. But as with warm fronts and cold fronts, they serve as focusing mechanisms for rain as well. Here's an example of a stationary front, again, on a surface map. Here's that same map that I showed earlier with the warm front. But again, notice that trailing cold front across Chicago and through the Central Plains, but then it actually stalls across Nebraska and into Colorado. So that cold front, which was moving southeastward, kind of loses its oomph and it stalls out. And part of the reason for that, in this case, you see just north of Texas, a low pressure area developing. So the circulation around that low is counterclockwise. So some of that southerly air kind of resisting the cold front and keeping it from moving farther south. So you'll often see lows developing along these stationary boundaries. And once that happens, oftentimes those fronts no longer are stationary because the low will force that stationary front northward, turning it into a warm front. But then south of the low, the part of the stationary front that was west of the low starts moving south, and that becomes a cold front. Those stationary fronts are now moving, and they've changed their classification, if you will. All right, the final type of front that we're going to talk about here is the one that often causes the most confusion, and that is occluded fronts. Basically, what happens with occluded fronts is a cold front catches up to a warm front. Now, cold fronts typically move faster than warm fronts, and part of the reason for that is warm fronts are moving slower because the cold air north of a warm front is cold, it's dense, it puts up a stronger fight, if you will, preventing warm fronts from moving terribly quickly. So those cold fronts ultimately start taking up or catching up with the warm fronts, and those trailing cold fronts push that warmer air aloft. And the way these occluded fronts are indicated, it's basically a combination of the warm front and the cold front. So rather than red and blue, we've got purple, and rather than the blue triangles and red semicircles, we've got purple triangles and semicircles, and they're all pointing in the same direction, again, indicating the direction of movement. In this case, more north than north-northwest. Here's an example of an occluded front on the surface map. The low pressure area, not too far from Martha's Vineyard, across southeastern Mass. The occluded front actually across the vineyard, maybe more Nantucket, but that purple line extending south and southeastward, and where it meets the warm front and the cold front, that's called the triple point. And it's not unusual to see new low pressure areas then develop there. But if we went forward in time with how this frontal system evolved, in all likelihood, you would see that occluded front gradually getting longer as that cold front continues to catch up with the warm front. All right, troughs. What is a trough? A trough is similar to a front. The biggest difference, at least at the surface, between troughs and fronts is that you don't have a significant change in air mass from one side of them to another. You may see minor changes in temperature. There might be differences in humidity or the dew point. That's a little bit more significant. Perhaps you've heard of the dry line. That's a phenomenon that'll often occur in Texas, often a precursor to severe weather. That's an example of a trough. Here in the Northeast, these are more common to be found on the backside of low pressure systems. And they're actually often associated with an upper level low. And we'll talk more about that a little bit later in the presentation. But troughs are associated with shifts in wind, so you don't get the tremendous change in air masses oftentimes, but you will get a change in wind direction. And again, it's often that change in wind direction, converging of winds, oftentimes at the surface, that produces the showery weather. That air converges at the surface, lifts up in the atmosphere, turns into clouds, and ultimately precipitation. Again, little temperature change with the troughs. So here's an example of a trough on a surface map. Again, that same low across southeastern New England with the occluded front and the cold front then well offshore at this point. But notice that dashed line that extends south-southwestward from the low. That's an example of a trough. In this case, again, there probably wasn't a tremendous change in temperature from one side of it to the other, but there likely is a shift in the wind direction and perhaps enough to create some showery weather as that system moves offshore. And again, these are associated oftentimes with upper level low pressure systems, and these are kind of a surface reflection of those upper level lows. So here's an example of an upper level low. This is from that same time, I believe. This is the upper level chart for 500 millibars. And this is a level that's often looked at by meteorologists. That's approximately halfway up through the atmosphere in terms of the pressure. And you notice the significant dip in the winds. So you see the arrows kind of diving southeastward across the upper plains, then moving more eastward over the Carolinas, and then right offshore, that sharp turn northeastward. So there's a sharp trough at the upper levels of the atmosphere of a lower pressure, if you will, in the center of that. And that surface trough that was on that previous map is kind of a reflection of that low pressure area aloft. Again, the arrow kind of pointing to the axis of that upper level trough over the northeast. All right, well, one of the other things that you can find on surface charts sometimes, the one that I was showing earlier did not have any surface observations on it, but especially when you get a more zoomed in view, something that's not looking at the entire contiguous United States, you might find wind barbs. And here's an example of how to read wind barbs in the Northern Hemisphere. In the top example, first of all, what this is doing is the flag, if you will, or the barb is kind of pointing in the direction that the wind is coming from. So it's pointing toward 270 degrees. There's a full barb at the end here, which is indicative of approximately, or not just approximately, but it's indicative of 10 knots, and then a half barb, which is 5 knots. So in this case, 10 and 5, 15 knots of wind coming from the west. Now, as you start getting into windier conditions and you get to 50 knots plus, you don't want to just keep adding all these full barbs on. It's just going to get way too busy. So then we turn it over to a flag, a triangle, and that's indicative of 50 knots. So in that second example, it's pointing to 180 degrees or a southerly wind at 50 knots. And then in the final example, we're starting to get into hurricane force conditions here. Hopefully you don't have to read any surface maps indicating winds of this speed, but from the southeast at 75 knots, you've got the full barb or the full flag indicating 50 knots, and then 2 full barbs and a half barb, 75 knots total coming from the southeast. The Beaufort scale, a lot of you probably familiar with this, of course, developed to try to estimate the wind speed in lieu of having an anemometer. And you, of course, estimate the winds by taking a look at the conditions around you and the effect that the wind is having on the sea state around you. In the example that I just showed previously with the 75 knots worth of wind, that's getting into force 12 and hurricane force conditions. Barometric pressure and using a barometer. Perhaps some of you have barometers on board. These can be helpful, not as much for, what is the barometric pressure or what's it saying. That in and of itself can only tell you so much. Although, if you've got relatively high pressure, let's say 1030 millibars, that would be indicative of a high pressure over you. And chances are that would be, lighter weather, or at least a lack of storms. You wouldn't have to worry as much about precipitation. But the trend of a barometer is more important than the actual barometric pressure. Is the pressure rising? If it is, then chances are you've got nicer weather on the way. If the pressure is dropping, well, then that's a different story. There's a couple of different rules. They're pretty similar. The 1, 2, 3 rule. If the pressure is falling 1 to 2 millibars in 3 hours, that's indicative of, well, maybe there's some unsettled weather coming. The 4, 5, 6 rule, a 4 to 5 millibar drop in 6 hours, that means a more significant change in the weather is likely coming. And of course, if it's dropping, chances are it's going to be a change for the worse. Buoy observations, perhaps some of you have used this. This is actually created by NOAA, the National Data Buoy Center, which is a part of NOAA. There are, of course, buoys worldwide, but the NDBC operates most of the buoys in the United States. These are quality controlled. So generally, this data is very good. There might be instances where the equipment might malfunction, but that's really the exception rather than the rule. The NDBC does a very good job of making sure that the equipment is working properly. Of course, in this particular case, the website would show the location of the buoy. And then if you click on the location of the buoy, you get perhaps something that looks a lot like this. You'd get a whole slew of data, perhaps including the wind speed and the gusts, of course, the direction that the wind is coming from, a significant wave height and period and the direction of those, air pressure, water temperature. Some of these actually even have cameras on them. So those can be helpful, especially in the daylight. The NDBC, they try their best to keep up with the maintenance of these. Sometimes the buoys might go adrift, especially in tropical situations. They tend to come on board and go drifting. And ultimately, eventually, the NDBC is more often than not able to recover them. But so it can be kind of hit and miss sometimes in that regard. But the US does a better job than most countries when it comes to buoys. You can also, using that website, look backward in time to see trends. Is the wind increasing or decreasing? Same thing with the seas. Same thing with the temperatures, of course. Ship observations. These need to be taken with a little bit of a grain of salt. Cargo vessels, cruise ships, sometimes private yachts will report wind speed and sea state, but it's not quality controlled. And sometimes it's estimated, but they'll report similar information as the buoys. Wind speeds, direction, of course, wave heights. Sometimes you'll get pressure, visibility, temperature, or dew point, but sometimes you might only get wind, or sometimes you might only get seas. And again, oftentimes these measurements aren't being quality controlled; they're only being estimated. Or one of the things that we have found here at Weather Routing, especially with larger vessels, such as large cruise vessels or large cargo vessels, in stronger winds, especially if those winds are hitting the vessel beam on, these are big vessels. Those anemometers are several stories up into the atmosphere, hundreds of feet up into the atmosphere. So not only are they sampling winds that are much higher, at a much higher level than what you would be experiencing nearer the sea surface, but sometimes those winds will actually funnel over the ship and result in even higher reports. So it's not unusual for us to sometimes see wind reports of 40 to 50 knots sometimes with vessels when they're in reality maybe only seeing 25 knots worth of wind. So again, they need to be taken with a more significant grain of salt versus buoy data. Here's another example of wind data that you can actually find access to online. And that's taken by satellites. In this example, it's ASCAP data. That's the name of the satellite. These are polar orbiting satellites. So those satellites, rather than circling around the globe over the equator, which is how you're used to seeing most of our satellite data in terms of what you see with clouds, these polar orbiting satellites literally rotate around the poles as the Earth kind of turns around them. They're at a much lower level in terms of their distance from the ground, so they can only see a smaller portion of the ground versus geostationary satellites. So in this example, notice how it's great. You can see the winds in the Gulf of Maine. You can see winds offshore of Rhode Island, and of course, Martha's Vineyard. But if you wanted to know what the winds were near Nova Scotia or near New York City, you're kind of out of luck. And these polar orbiting satellites go around the Earth twice a day. So you might be lucky. You might, for your area of interest, you might get 2 samplings from these satellites. But sometimes you might get none. It's kind of the luck of the draw. All right, let's talk about radar. Radar, of course, as a lot of you are aware, indicates precipitation, rain, snow, sleet, things of that nature. It shows the intensity and movement of those features. Of course, if you animate the radar, the quote unquote hotter the colors, the darker oranges and the reds, those indicate higher precipitation rates. And along with that, once you're starting to get into the reds, you in all likelihood are looking at some thunderstorm activity. Now radars, and again, here's an arrow. This is offshore of Texas to the south of Louisiana, showing some thunderstorm activity that was probably drifting northward in the direction of Louisiana. Now radars are ground-based. They're not like satellites where they're based way up in space. They are based near ground level. For Martha's Vineyard, they're actually based near the National Weather Service office in Taunton, Mass. There's 160 of them strewn all about the US and the territories. And again, the US is one of the world leaders as far as radar data is concerned. But the availability of that data around the globe tends to vary wildly. Now radars, because they're based at the ground, only have a certain range, and that's 290 nautical miles from where the radar dome is located. There isn't any coverage beyond that. The problem is, as the radar beam shoots out from the radar dome, it's at a slight angle, and of course, due to the curvature of the Earth as well, once you get out beyond a certain distance, that radar beam is actually shooting over the top of the clouds and the precipitation. But one of the more significant developments over the last 30 years or so was the development of Doppler radars. And the big improvement there is the ability to see winds within areas of precipitation, which of course can help with locating tornadoes, water spouts, and straight line wind damage, the potential for straight line wind damage. Here's an example of a tornado on radar. And you've probably heard at times about the hook echo. In the image to the left here, you can see kind of the classic hook echo just off of Goderich here. And this is actually a Canadian radar. The image on the right is from the same system, but it's the Doppler radar. And what the Doppler is measuring is not just the winds, and it doesn't give you a perfect picture of the winds, but what it does is it measures the component of the wind that is either heading toward the radar site or away from the radar site. And when you see stronger winds that are heading to and away from the radar, especially at a high rate of speed, that's indicative of a circulation and the possibility, at least, of a tornado. Again, here's the arrow pointing at the hook echo on the left side. All right, satellite imagery, I already kind of touched upon this. Unlike radars, satellites are, of course, based up in space. This here is an image of the GOES 13 satellite. And I believe we're actually up to 15 or 16 now. For every generation, if you will, of satellites that go up into space, it gets a new classification. So this was actually 1 or 2 generations ago, the GOES 13. But these particular satellites, the ones that take the imagery of the clouds, those are geostationary orbiting satellites. They sit right over the equator, and as the Earth turns, these satellites turn with the globe. So they stay over the exact same spot. These are used to help determine sky conditions. And there's there's a multitude really of different wavelengths that the satellites are able to read, the most common of which, and the ones that you're most familiar with, just from seeing even the TV weathermen, the meteorologists, is visible satellite infrared, and sometimes you might see some water vapor imagery at times. Of course, the satellite can be great for finding areas of fog, clouds, of course, thunderstorms. It can also be helpful in finding outflow boundaries, which is something that you might not necessarily see with radar imagery. All right, let's talk about some of the pros and cons of the different imagery. Visible satellite imagery, it's kind of the best, quite frankly. It's more or less literally what you would see if you were looking down yourself from that satellite. It is measuring the visible satellite imagery that gets reflected from the Earth back up to the imagery. So it needs to be illuminated by the sun. Once the sun sets, no more visible satellite imagery. But it gets a very good resolution. I think we're at a ½ kilometer of resolution now. So it does a very good job of seeing the structure within thunderstorm activity. And again, this is from GOES 13. So the satellite imagery is actually even improved beyond this particular image. But here's a view from the Caribbean Sea, some of the brighter whites indicating some of the stronger thunderstorms. But notice this area kind of just north of the cluster, this straighter line that goes almost due east to west. That's an outflow boundary. So what happened was the stronger thunderstorms, the larger area thunderstorms, produced a lot of cold air that then drops down through the atmosphere. It hits the water and then rushes outward, in this case, pushing north. And that outflow boundary can sometimes catch mariners by surprise, because there might not necessarily be a thunderstorm with the outflow boundary itself. Again, here's another example of visible satellite imagery. I showed you the radar earlier off of Texas and Louisiana. Here's the satellite from that. Again, this is visible satellite imagery. And again, you see some of those brighter whites. Those are, and there's kind of a texture to it, if you will. That's indicating some of those clouds pushing higher up into the atmosphere and creating thunderstorms. Fog, and a view here a little bit closer to home. The Gulf of Maine, southern New England, well, all of New England. Visible satellite imagery is extremely helpful for finding fog. It's a lot more difficult to find fog with the other forms. Look for smooth or gray areas. It doesn't tend to be as bright white. And if this were animated, you would see the movement. There's a fog bank near and east of George's Bank there, over to the south of Nova Scotia. Infrared imagery can pick up where visible satellite imagery leaves off. At night, you're going to need infrared imagery, or at least one of the other forms. But it's measuring temperature, and it can measure the temperature of the bare surface, the bare ground, and it measures cloud temperatures. The resolution is not as good as visible satellite imagery, so it's a little bit more challenging to see fine scale features, but it is available 24/7, so that's a great feature to have at night. Clouds, thunderstorms in particular, when they go higher up into the atmosphere, of course, the higher you go up, the colder it gets. So when you're looking at the very tops of clouds, you see extremely cold temperatures. And in this case, where we're getting the brighter oranges and the reds, again, thunderstorms in this view indicating thunderstorms near the Yucatan. And again, kind of looking up toward Texas and Louisiana, this is that same time frame. Some of those oranges there, again, indicative of thunderstorms that I showed you earlier. All right, let's talk about how you can read the clouds and the progression and the movement of those clouds to give you an idea of what's happening. Of course, ahead of approaching systems, clouds change. And you can read those changes to help you decipher what to expect over the next 12 to 24 hours. If you, for example, missed the weather forecast that morning. You've all heard the saying, of course, red sky in the morning, sailor take warning, red sky at night, sailor's delight. Cumulus clouds, these are more indicative of fair weather. They do indicate some instability in the atmosphere, but it's really confined to the lowest levels of the atmosphere. So you might, in a situation where you see these cumulus clouds, chances are you're not going to get any precipitation, or if you do, it's going to be brief. but it's a sign of shallow instability and limited amounts of moisture in the lowest levels of the atmosphere. But in these scenarios where you see these types of clouds, even if the wind isn't terribly strong, there's some mixing going on in the atmosphere. So you might be more likely to get some puffs from those clouds in those situations. In the opposite scenario, where there's a lot more moisture and there's a lot more instability throughout the atmosphere, you can get a cumulonimbus cloud, such as what we're seeing here. These are far more significant, of course. These are thunderstorm clouds, and you could get the potential, at least, for water spouts, and certainly the potential for some heavy rain and lightning with those. Now, let's talk a little bit more about the progression of clouds ahead of a system. What happens with a low pressure system is warmer air is trying to ride out well ahead of the actual low. And again, I kind of talked about it earlier. Warmer air is lighter, it's less dense than colder air. So what happens is as it tries to come north, it has to ride over the top of the colder air near the surface. So it's going initially way up in the atmosphere. And all the clouds that you see here, these are cirrus clouds. These are actually made up of ice. And these typically would occur about 24 hours ahead of a low pressure system. What happens with time, as those clouds progress, they tend to gradually thicken with time. And they also tend to lower in altitude with time. You get a lowering base of the clouds. These are altocumulus, and they're indicative of precipitation within the next 12 hours or so. Finally, the low pressure system is all but upon you. Nimbostratus clouds. Precipitation is imminent, or it's already occurring. Of course, when the precipitation is falling, you get lower visibility. You might get fog. The humidity levels, of course, extremely high. But once that visibility starts to increase, the precipitation will start to decrease. Our final topic for tonight is ocean currents. And I talked about it earlier about how the Earth doesn't like inequality when it comes to energy. It's always trying to redistribute the energy around the world. And the atmosphere is a huge part of it, but the other huge part of it are the currents. And this is going to be, when I'm talking more about oceanic currents here, as opposed to tidal currents that are driven more by the changing in the tides. These features vary considerably with weather features. For example, if you've got a strong wind over several days, that can actually create an ocean current or adjust a pre-existing current. But more significant currents like the Gulf Stream, the changes from that tend to be much slower to occur, and those are affected to a much lesser degree by atmospheric events. But ocean currents, as you may be aware, can be quite variable over short distances. So here's an example of ocean currents, as well as the Gulf Stream. This is actually an image. We've got an online service that we offer, seaweather.net. This is an image taken from there. But of course, the northeast coast and the Canadian Maritimes, you can make out the main current of the Gulf Stream from just offshore of North Carolina, and Cape Hatteras kind of moves northeast and then turns eastward around 38 north and then off into and through the central Atlantic. But you'll get little eddies that will break off from the main branch of the Gulf Stream and drift either northward or southward, kind of redistributing colder and warmer waters as you could see. But if you're going trying to get from point A to point B, let's say you were trying to get to Bermuda from the Vineyard, you're with those eddies, you're going to want to try to take advantage of them wherever you can, or at least minimize them if you find yourself in an opposing current, because 1 to 2 knots of opposing current obviously is significantly different than 1 to 2 knots of following current. Finally, here's a look at sea surface temperatures, again, from that website I referenced. You can very clearly make out some of the darker reds in the core of the Gulf Stream, the warmer waters with that. And some of the eddies, especially the warmer eddies to the north, where the warmer waters of the Gulf Stream have kind of broken off and shifted to the north. So with that, I will turn things back to John and see if we've got any questions here.
Yeah, I'm going to look for questions in the chat box if anybody has any, but also if you'd like to ask a question, please unmute yourself. I think most people are muted, and we'll try to keep it under control here. In the meantime, I don't see anything yet, Brian, but I just wanted to ask myself, as coastal storms come up the coast and go by here, or especially big lows like hurricanes and things,
Mhm.
we're always hearing this term. It's close to the benchmark, or it's east of the benchmark.
Mm.
Do you know what exactly where that benchmark is?
It's funny that you mentioned that. I actually do need to look that up. Especially as somebody who grew up in southern New England, I'm kind of ashamed that I don't know it off the top of my head. But bear with me just a second. It's basically southeast of New England, and I believe it's 40 north and 70. So southeast of Martha's Vineyard. So, and I think they use the term the benchmark because anything that goes north and west of the benchmark is more likely to have direct impacts on southern New England, whereas anything that goes south or east of the benchmark is more or less a miss, if you will, or the effects of it are likely to be less significant. But I'm pretty sure it's 40 north and 70 west.
Okay. Yeah, I just hear it all the time on the weather reports, and I've never quite nailed down where it was.
I think you'll hear it a lot out of the National Weather Service out of Taunton. I think those guys and girls will use it quite a bit.
Okay, great. Somebody is asking if this will be recorded and available later. And yes, we are recording it. And we will, with permission of Weather Routing Inc., make it available on our website. Probably not until tomorrow, because it takes a little bit of time to process the recording.
Yeah, and I'll just say straight away that yeah, you definitely have our permission. Feel free to share it as you like.
Great, thanks. And let's see, we're getting a thanks for all this info. What's the better indicator for a tornado, radar or Doppler?
Good question. Yeah, they're both helpful, but I would say the Doppler effect and wind velocity is the more significant, the better indicator. Because sometimes even you can get kind of that classic hook signature, maybe not to the extreme that that one example that I showed you, but you might see kind of that shape in the precipitation field of the radar imagery. And if you look just at that, you might get a little bit nervous. But if you don't have the actual circulation, if the atmosphere isn't spinning, chances are there's not a tornado with that. So ultimately, the Doppler is the much better indicator, I would say.
Another question is, what does the radar actually measure? I'm not certain what they mean there. And what's DBZ?
Yeah, it's actually what it's measuring is it's called reflectivity, and the DBZ is basically decibels. And so what the radar is doing is it's sending out these pulses, and I don't know the exact figure, but it's in the thousands of seconds. And what it does is, so those pulses are going out from the radar, and of course almost instantaneously returning. And so what the radar is able to do is it knows, of course, how much energy went out. It measures how much gets reflected back. And so the reflectivity is literally measuring how much of that energy gets reflected back. So if it's getting a lot of energy back, that means it's hitting a very large raindrop or a hailstone or whatever the precipitation might be. And so it knows if it's seeing a huge amount of energy coming back, then there's some pretty large things falling out there. The Doppler, what that is doing is it can actually measure, again, it's not a perfect measurement of wind, but it's measuring the speed at which that beam of energy is getting returned. So if, I'm going to try to do my best to kind of visualize it here. So let's say it's measuring a raindrop, and of course the raindrop is dropping, but there's also, some movement on a plane, either toward or away from the radar. And so as that beam is kind of hitting it, so let's say it's moving this way slowly, as it's hitting it, it hits it at one speed, but because then it kind of reflects off at a different speed, that radar is able to tell that difference and kind of extrapolate the speed of that object and how quickly it's either moving toward or away from the radar. It's pretty fascinating stuff.
That's great. Any other questions? Not seeing anything in the chat here. Feel free to jump in. Okay, I guess that's about it. Well, thank you, Brian, so much. Really enjoyable. And thanks everyone for participating in our winter lecture series. Unfortunately, I'm almost sad to say it's our last one of the winter, we're calling it. And our warm weather is telling us that spring is coming. And we hope that we'll see a lot of you in our summer programs here on the waterfront. We anticipate running the Vineyard Cup July 10th and 11th, though it's not 100% certain yet because we are working on the plans right now. But that is our intention at this moment. And of course, weather routing will be there with us to provide weather forecasting for the Vineyard Cup Regatta coming back this summer. And we hope everything else sailing wise will be back in full operation this summer. Our programs will be with some modifications, but we've got a lot of people signed up, lots more coming in every day, and some courses are actually nearly full up. So don't forget to make your reservations. Thanks again for your donations to Sail Martha's Vineyard. Very generous, and that's helped us put on these programs for you this winter. Hope to see you all soon. And if nothing further, we're going to say good evening. Thanks.
Thank you.
Thanks, Brian.
You're welcome.
Good night.
Good night.
Good night.
Thanks.